and I need Faisal make host. Okay.
Yep.
And from here, what do I need to do? Just need to do this. Yes, that's good. And what do we do now? This is HDMI, right?
Yes. Yep. That's the one. And the representative you probably
This
want
one
the
is okay.
Okay.
Perfect. Thank you.
No problem. Just give the sound a test. Make sure your mic's not muted. You should be good to go. If you need to handle the amounts.
Thank you. Hi, Faisal. Is it working? Yeah. And how's the audio? Is the audio okay? Okay, so we're working through chapter 3. We're doing nodal analysis. Just as a reminder, what we're doing here is you're following those steps. You're looking at your circuit. You're going to locate all the nodes in your circuit. One of those nodes you're going to select as the reference node. You're going to label all the remaining nodes, 1, 2, 3, whatever, with voltages V1, V2, V3, and so forth. You're going to write a KCL to each one of these in terms of those of the voltage, right? We solved a few problems. We saw, like, for example, here, you take this ground node, you have V1 and V2, you're going to write a KVL at V1, a KVL at V2, and you solve these two equations simultaneously. We did that last time. And this is an example. We solved this one. We also solved this one. Now, we're coming to a problem. How can you write KCL in the presence of a voltage source? Now, to write a KCL, you have to know what is the current that you have in that particular branch. Because KCL tells you or gives you a relationship between the currents entering a node and currents leaving the node. So if you know the currents, or you have a way to express the current, then you per node. I'm going to form a supernode like this, and this is the definition. Supernode is formed by enclosing a voltage source connected between two non-reference nodes and any elements connected in parallel with it. That's the definition of a supernode. And remember, when we defined KCL, we mentioned that you can apply KCL at a node, or you can apply KCL at a closed boundary. So this is exactly what we're going to do here. I'm going to apply KCL at the supernode. So looking at the supernode like one big node, or this boundary, and we're going to apply KCL there. We're going to say that the sum of the currents flowing into the supernode has to be equal to the sum of the currents flowing out of the supernode. So can somebody tell me what are the currents flowing into the supernode? Yes. I1 and I4 are flowing into the supernode. What are the currents flowing out of the supernode? Yes. Okay, so we can write I1 plus I4 equals I2 plus I3, right? That's KCL at the supernode. Now I'm going to express each one of these. I1 is V1 minus V2 over 2. And be careful with the polarity. I didn't say V2 minus V1. I said V1 minus V2 because of the direction of current flow in the resistor. I4 is V1 minus V3 over 4. I2 is V2 minus 0 over 8. And I3 is V3 minus 0 over 6. So now I have an equation that I was able to write around my supernode. Okay. What other equations can I write? Look, you need 3 equations here because you have 3 unknowns, right? V1, V2, and V3. So this is one equation. I'll tell you what you can do. You see that? You see that voltage source that's there, that's like this 10 volt source? By definition, we know that a 10 volt source maintains 10 volts across its terminals. So if the bottom terminal is connected to 0, then the top terminal has to be 10 volts higher than 0. That's why from this voltage source, from this 10 volts, I already have the solution for V1. V1 is not an unknown anymore. V1 is effectively 10 volts. Can you see that? Okay. So this voltage source, instead of being a problem, it actually became an answer. Because I chose my ground node, and then I put V1, V2, V3. I have a voltage source that maintains V1 at 10 volts. So there you go. V1 is already, it's kind of given. Okay, so I have V1 equals 10 volts. And I have this other equation that I wrote around my supernode. You still need a third equation. And the third equation, you're going to get it from the supernode. So every time you have a supernode, you're going to look inside the supernode, and that's where you're going to get your additional equation. So look at that. What does this 5 volt source tell us? It tells us that it maintains a difference of 5 volts, precisely 5 volts, between its 2 terminals. So look at it. What does it tell us about V2 and V3? Yes. V2 minus V3 equals to 5 volts, exactly. Can everybody see that? Okay. So when you find current sources, you use the normal method. That's what we did before. Sum of the currents flowing in equals the sum of currents flowing out, and you write in your KCLs. If you have voltage sources, you cannot write KCLs directly. So what are you going to do? You're going to apply the method. You're going to choose your ground or your reference node. You're going to label the other ones V1, V2, V3. If your source is connected or is connecting one of those nodes to ground, like your 10 volt source here, then you already have the solution for that node. If you have a source that connects 2 non-reference nodes, then you create a supernode, you write your KCL at the supernode, and you look inside the supernode for your additional solution, your additional equation. So the extra equation is V2 minus V3 equals 5. There you go. You have 3 equations. And in fact, they're not really 3 equations because V1 equals 10 That's already a solution. You're going to insert that in your equations, and you're going to find that solving them is not difficult now. Any questions about the supernode? Okay. Here, there you go. This is an example. You have a circuit. You're given the reference node. You have two nodes, V1 and V2. You have two current sources and one voltage source. Let's see how we're going to solve this. No, sorry, this is minus and plus. Okay, nodal analysis. This is a reference. These two are labeled V1 and V2. These are your two unknowns. First equation, can you write KCL here? You have this current, that's 2 amps flowing in. You can write a current here, V1 minus 0 over 2. You can write a current there, which is V1 minus V2 over 10. But then you're stuck with this one. So you're going to have to use a supernode. Now remember the definition of the supernode. It said, I'm going to actually go back to that. I want you to see it. The supernode is formed by enclosing a voltage source connected between two non-reference nodes and any elements connected in parallel with it. Did you see this line? Okay, so let's see how we apply that. So my supernode is actually going to enclose this parallel element like that. Okay. And I'm going to write one KCL equation at the supernode. Sum of the currents flowing in equals sum of the currents flowing out. So I have currents flowing in I have a 2 amps flowing in here, and then I have all the others are flowing out. So I have this one flowing out, that's V1 over 2, that's V1 minus 0 over 2, plus the second current is V2 over 4, plus I have 7 amps flowing out. Okay, so there you go. This is the first equation. You can rearrange that. That's your first equation. Any questions? A reference node is not an unknown. The reference node has a voltage that's assumed to be 0. There's a question here, somebody's asking, what is the difference between reference node and non-reference node? You have a number of nodes, and we defined the concept of a node voltage, which is how much voltage or at what level of voltage or level of energy is any node compared to a reference. So to make the method work, we have to pick one reference. We're going to make that our reference node, and we're going to assign a voltage of 0 to that one. So this node, which is the bottom node here with this symbol down there, this is assumed to have 0 volts. So you don't need to solve for that one. Okay. So that's KCL at the supernode. I need another equation. As I mentioned, to get the other equation, you have to look inside your supernode. So what can you say when you look inside? Your equation has to be in terms of V1 and V2. These are your two unknowns. So what would the second equation be? Suggestions? How am I going to get my second equation? V1 minus V2? No. Look at the polarity. It's V2 minus V1. You see the plus and the minus signs. Tells you that V2 is at a higher voltage than V1, and that difference is 2 volts. So the second equation is V2 minus V1 equals 2. That's your second equation. Okay? So now you need to solve these two equations simultaneously. I mean, we can do it from here. I can say V2 equals V1 plus 2. So 2V1 plus V1 plus 2 equals minus 20. 3V1 equals minus 22. That gives you V1. Plug it in here, gives you V2. These numbers don't look very nice, so I hope I didn't make any mistakes somewhere. But anyway, you can revise that. This is 2 plus V1 over 2 over 4. That's 7. Okay. 2V1 plus V2 equals minus 20. This looks good. V2 minus V1 is 2. V2 is V1 plus 2. 2V1 plus V1, 3V1 plus 2 equals negative 20. Well, looks good. So in that case, V1 equals minus 22 over 3. Okay. Volts. You put that in here, you get V2 equals plus 2, which is 6 over 3. Okay. I hope there's no errors anywhere. Anyway, but I mean, you get the idea, right? That's the method. How you write KCL around a supernode, and how you look inside the supernode to find your second equation. I'm going to do one more. You can also use the concept of supernodes if you have a dependent source or a controlled source. So here you have a circuit where you have, see those 1, 2, 3, 4. You have 4 nodes other than your reference node. And then you have 2 supernodes because of the voltage sources, and one of them is a controlled source, 3Vx, and they're giving you your Vx. So let's see how we're going to generate those equations. Okay, I'm not going to redraw the circuit. I just want to write first KCL around supernode 1. Okay, so if you look at supernode 1, I may make some marks here. let's say this is the direction of this current. That's the direction of this current. This one is also going like that. And like that. And I have one more here. So first supernode, you have the first current, that's V1 minus 0 over 2. This is going out, right? I have one current flowing in, which is my 10 amps. This one is going out. The top one in the 3 ohm is also going out. That's V1 minus V4 over 3 plus V2 minus V3 over 6. Okay. So I have one current flowing in from the current source. Your 10 amps is flowing in. And you have these 3 currents flowing out. V1 minus 0 over 2, V1 minus V4 over 3, and V2 minus V3 over 6. So this is your first equation. I'm going to write KCL at the second supernode. The supernodes. From supernode 1, 20 volts, that's the difference between V1 and V2. So you have V1 minus V2 equals 20. That's your third equation. And your fourth equation is V3 minus V4 equals 3Vx. Okay, Vx. Now I have a problem. I'm supposed to have 4 equations in 4 unknowns, which are V1, V2, V3, V4. But here I have in one of those equations an additional unknown, which is Vx. I have to get rid of this one. So what do I do with Vx? How can I get rid of this additional variable? Can I express Vx in terms of the other ones? Yes?
V1 minus V4.
Exactly. Yeah, Vx is in fact equal to V1 minus V4. Okay? So you just put this in here and you get 4 equations. So once you have 4 equations and 4 unknowns, the rest is math. Okay? And you have to know how to solve that. There are many ways to solve 4 equations and 4 unknowns. Well, here this is V1 minus V2 equals 20. You can say V1 equals 20 plus V2, and you kind of remove V1 from everywhere, and you have something in terms of V2. Do the same thing here, V3, V4, and V1. So you kind of try to eliminate one of them, and you end up with 2 equations and 2 unknowns, which you have to solve, and you keep kind of, you know, substituting in the other equation. So this is just math. You can find the full solution in the book. And I'm going to move on. Mesh analysis. Remember we said that in this chapter we have two particular methods of analysis. One is called the nodal analysis or the node voltage method, which is the one we've been looking at. This one is called the mesh analysis or the mesh current method. So what does this one tell us? First, we're going to define a mesh. A mesh is a loop which does not contain any other loops within it. It means it's an inner loop, okay? So how many loops do I have in this circuit? How many loops do you see in that circuit? No, loops. You have two meshes. But how many loops? You have three loops, okay? Because you have the outer loop, you can go around. A loop is any enclosed path, right? So you have three loops in this circuit, but you only have two meshes, which are the inner loops. So in this particular analysis method, we're looking at the meshes, only at the inner ones, which makes it actually easier because you don't have to try to go around and figuring out how many other loops you have. You just look at the inner ones. So you have two meshes here. We are going to define something called, well, we know what are branch currents, right? Branch currents are the currents that flow through branches. This is the current that we're talking about. We're going here to make it's kind of a mathematical modeling tool. We're going to call it a mesh current. Mesh currents, and I have to know, you have to be aware of that. Mesh currents don't really exist in circuits. We don't have something called a mesh current. This is a mathematical modeling tool that we're using, exactly like we defined something called a node voltage. And we said that a node voltage is not something that really stands alone because voltage is always a difference between 2 points. So to get around that, we said one of them is our reference. We label it as 0 volts, and everything else, any node voltage, is the voltage compared to that reference. So here we're also going to do something. We're going to define something called a mesh current. Now look at that. You have your currents, capital I1, capital I2, and capital I3. These are the branch currents. These are the currents we're used to, we understand these. The current is flowing inside your elements through your wires. Okay, those branch currents, they come together at a node, and you have your KCL. The ones that are the small ones, small I1 and small I2, we call them mesh currents. And we just imagine that you have a current that keeps going round and round and round inside a mesh. Okay, so here, in fact, you have those two mesh currents. One current, small I1, keeps going around in the first mesh, and the other one, small I2, goes around in the second mesh. Okay, you had a question? No. I mean, it's not about capital or small. I mean, we could have called them IA, IB, the mesh currents instead of, I1, I2. They just decided to do that. It doesn't matter. So the idea is this I1 and I2 that we have here, those mesh currents, this mathematical model, this kind of tool that we're going to use is going to just make it a little bit easier for us. And you're going to see that in when we're solving problems. Because if you look at the branch currents, you have three branch currents, right? Capital I1, capital I2, capital I3. And if you want to write equations based on the branch currents, you'll be able to, but you're going to have three unknowns because we don't know those. When we're using the mesh currents, it's kind of, they're related, and I'm going to show you how they are related. But we kind of reduce the number of equations that we have in a problem. So how do we find this relation? Look at that. What is the current flowing through your R1 resistance? In terms of the branch currents, R1 is carrying the current capital I1, right? But in terms of the mesh currents, what is the resistance R1 carrying? Small I1. That's the current that's flowing around in that mesh, okay? So we're saying that small I1 and capital I1 are the same. So small I1 is equal to capital I1. Same thing for small I2 and capital I2. However, look at R3. Any branch that is shared between two meshes. This is where we find the difference between mesh currents and branch currents. If you look at this resistor R3, you have this capital I3 flowing through it, right? That's the branch current. It's one current flowing like from top to bottom, right? Vertically downwards. But now, what are the currents flowing through R3 if you're contemplating the mesh currents? You have both mesh currents flowing through I3, right? You have small I1 flowing. It's going round and round in mesh 1, so it's flowing through R3 from node B to node E, from top to bottom. But at the same time, you have the mesh current I2, small I2, that's also like assumed to be going around the mesh. So this one, I2, small I2, is flowing upwards, right? It's flowing from node E to node B, okay? And you have this relationship because one of them is flowing from B to E, the other one is flowing from E to B, so their difference is going to give you the actual branch current, which is really physically flowing in your branch. So we put this relation that you have in the bottom there, capital I3 is equal to small I1 minus small I2. Okay? Now, why did we choose small I1 minus small I2, not the opposite? Why didn't I say small I2 minus small I1? Why didn't I add them? Why did I subtract them? How can I relate that? Any suggestions? Anybody see any relation between my mesh currents and my branch current in resistor R3? Well, the whole point, you have to remember that what physically happens in your circuit is the current flowing through the branch currents. That's what's real. That's the physical, right? So I'm trying to model that using my mesh currents as a modeling tool. So I want to say, how do I relate this current capital I3 with those two currents flowing round and round like that? Now, the idea is I3 is flowing in the same direction of small I1, and small I2 is flowing in the opposite direction. So I3 is equal to I1, small I1 minus small I2, okay? Because the difference between these two mesh currents is going to be a current in the direction of capital I1, okay? So this is how you do that. So just, you have to be careful with the direction of flow of your currents when you're doing that. Mesh analysis, or we call it the mesh current method. You're going to apply these 4 steps. This is how you're going to apply the method. Number 1, you assign mesh currents to the n meshes. Okay, so you have n meshes. You're going to assume that you have those mesh currents flowing around, and you assign them, I1, I2, I3, I4, whatever. Now, the current direction is arbitrary. You can assign them clockwise or anti-clockwise, but it is easier to adopt a specific direction for all of us. Like, can we say, you know what? Let's all assume clockwise so we can compare our solutions, so we don't get confused. Because if somebody decides to assign them anti-clockwise, and you're careful on really making sure that you're following all the methods right, it's going to work. And even if you assign one of them clockwise and the other one anti-clockwise, it will still work if you're careful when you're writing your equations after that. But just so that we don't end up messing the whole thing, let's agree to all use a clockwise direction for our mesh currents. Point number 2, you're going to write a KVL to each of the n meshes. You're going to go around every mesh and you're going to write a KVL in terms of the mesh currents. You're going to produce a number of equations in terms of the unknowns being your mesh currents. That's what you're going to solve for. And then you're going to solve your n simultaneous equations. You're going to get your mesh currents. And then the final step, once you have the mesh currents, you have to generate the physical currents, the real ones, the branch currents from the mesh currents. And how do you do that? Like we did it here. You're going to say capital I1, that's a branch current. It's equal to small I1 because that's the only current that's flowing there. Capital I2 is equal to small I2. Capital I3 is equal to small I1 minus small I2. So you have to generate your mesh, your branch currents from the mesh currents. Okay, so let's see how the method is going to work. Example. So that's actually the same circuit. We're going to follow it step by step. First step, you're going to assign those mesh currents like that, okay? And then step number 2, I want to write KVL around each mesh. Now look at that. I'm going to go around the first mesh. I'm going to start from the corner F. If I go upwards, I'm going from F to A, I'm going to go through the voltage source V1. Is that a voltage rise or a voltage drop? I'm going from here to here. This is not a current, that's my direction of walking through my loop to write KVL. So here, from here to there, is that a voltage rise or a voltage drop? Somebody said something? It's the voltage rise or voltage drop. I heard somebody there say something. Okay. It's a voltage rise. Okay. So you have a voltage rise of V1. And then I'm going to proceed from here to here. Is that a rise or a drop? That's a drop. How much of a drop is that? Ohm's law. I1 times R1, exactly. And then remember, when you have a current like this I1 that's here, but be careful, we're using small I1, okay? Because we're writing it in terms of the mesh currents. So if you have a current like small I1 flowing in that particular direction, remember in a resistor, the current always flows from the higher voltage to the lower voltage. So you get a drop, which is I1 R1. Okay, I need to continue. I'm going to go from here to here now. The third one, is this a rise or a drop from here to here? That's again a drop. If you're following, I mean, if you put plus and minus from top to bottom, let me do that. I'm going to write a plus here. This is a pain, sorry. I'm not going to write that. Okay. I have here a plus sign and assume I have here a minus sign. Okay. So you have, in terms of small currents I1 and I2, you have a drop due to small I1 minus small I2, because that's the resultant of both of these flowing downwards. So you have this drop, which is equal to small I1 minus small I2 times R3. And then you don't have anything here. Okay, so that concludes your KVL. And that's your first KVL equation. Okay, let's write the second KVL equation. I'm going to go around mesh 2. Now, what am I going to do? I'm going to start here. I like to start at this corner, the corner E. If you go upwards from E to B, look at that. Because I put plus and minus I'm going to assume I have a voltage rise here, okay? If I'm going upwards from E to B, and the rise is equal to I1 minus I2 times R3. Okay? So that's what you have. That's the first part. The second part, from here to drop, which is equal to you get from these two equations and two unknowns. Okay. If you say I2 minus I1, it means you have this direction called that, then you're also assuming plus or minus in this direction. Okay, so let's do it like that. If you that would be a drop going from here to here. Another drop, which we found out to be I2 R2, and then you have the voltage source, which is compare these two and you say, okay, I'm going to put plus minus. I did originally, I kept it like which assumed is actually I1 minus I. I2. So if you're writing K2, the drop plus V2. Okay. So these two are the same. If you're careful how you're writing them, once you solve these equations simultaneously and you find the two values for small I1 and small I2, you need to find the branch. So your branch currents are going to be like capital I1 is the same as small I1, capital I2 is the same as small I2, and capital I3 is I1 minus I2. Okay. This is an example here. Find the branch currents. See, they're very specific here. They're saying find the branch currents using mesh analysis. So we're going to do the mesh analysis. We're going to end up with mesh currents, but we still have to find the branch currents because that's what is the real current, the physical one. Okay. I'm going to assume my two mesh currents clockwise as we agreed. And I'm going to go around each one. I'm going to write a KVL for it. So KVL around loop 1 or mesh 1. So I'm going to start from here. I'm going like that. I have a voltage rise of 15. And then this part here. Okay? And then I continue from here to here. What do I get? Now this is the tricky one. I'm going to assume a drop, which means I'm assuming that the current here is I1 minus I2, right? In that direction. So I have a drop of 10 I1 minus I2. And then finally, I have the last element from here to here. That's again a drop of 10 volts. Okay? If you want to rewrite that, 15 I1 minus I2 equals 5. Okay? That's our first equation. Let's do KVL around loop 2 or mesh 2. So again, I'm going to start from the bottom left corner. Yes? Oh, yes, sorry. Absolutely. What did I do? Thank you. You're absolutely right. So it's 15 equals 5 I1 plus 10 I1 minus 10 I2 plus 10. Exactly. Yeah. You have to have brackets, right? And then from here to here, I have a drop given by small I2. So I have 6 I2. And then finally, from here to here, I have 4 I2. Another drop. So what do we have? It's 20 I2 minus 10 I1 equals 10, right? That's the second equation. Obviously, you can kind of rework those equations. So this one, you could say this is 3I1 minus 2I2 equals 1. Okay.
And this one you could say 2i1 minus, sorry, 2i2 minus i1 equals 1. Okay, so two simple equations. So from here, 2i2 equals i1 plus 1. I'm going to use this one in here. So I have 3i1 minus 2i2. So minus i1 plus 1 equals 1. So 3i1 minus i1, that's 2i1 minus 1 equals 1. 2i1 equals 2. I1 equals 1 amps. 1 amp. From here I can get I2. I'm going to use this one here. I2 equals I1 plus 1, which is 1 plus 1 equals 2. So I2 equals 1. Well, this one also is equal to 1 amps. 1 amp for some reason. If you have a situation where the two mesh currents are equal, it's going to create an interesting Okay. So if you have these two mesh currents, what would be the value of the branch currents? I1 is equal to small I1, that's 1 amp. I2 equals small I2 equals 1 amp. And I3 equals I1 minus I2 equals 0. Okay, there you go. Another example. Use mesh analysis to find the current I0 in the circuit. Okay, so look at that. You have 3 mesh currents, small I1, small I2, small I3. And you have a dependent source for I0, and you're given the I0 being this current flowing vertically through your 10 ohm. We want to find how much this I0 is. Okay. Three mesh currents, I1, I2, I3. Let's write 3 KVLs. KVL around loop 1. Start from here. You have voltage rise like that. That's 24 volts. And then you go from here to here. That's a drop, right? Now this drop is equal to 10 I naught. I'm going to write it like that for now. Okay. You have a drop here. You have a current called I naught. So this drop is 10 I naught. And then from here to here, that's my first equation. Second loop. I'm going to go from here. Now, because I have this current called I naught flowing in this direction, I'm going to put the plus and minus like that. Plus and minus, that's the direction of drop that you would get because of this current I naught. So if you're going in this direction, if you want to write your KVL in terms of I naught, then you have a rise here. I'm going to do that. 10 I naught, that's a rise. And then I keep going like this. That's a drop of 24 I2. And then from here to here, notice you have two mesh currents now. So if I'm going in this direction, if I'm assuming that's a drop, then I'm assuming I have a current flowing like that, which is I2 minus I3. So the drop is equal to 4 I2 minus I3. That's the second loop. KVL at loop 3. Again, I start in the bottom here. I'm going to go like that. If I want this to be a drop, then I'm assuming that I'm having a current that is in the same direction as I3 and opposite to I1. So it's I3 minus I1. That's a drop, right? I3 minus I1 times 12. And then from here to here, that's to be a drop. That's 4 times, if you're going like that, that's in line with I3 and opposite I2. It's 4 I3 minus I2. And then last element, you go like that, that's again a drop of 4 I naught. So this is equal to 0. So here you go. You have 3 KVL equations in terms of your unknowns. Small I1, small I2, small I3. The hitch here is this capital I naught, because 3 equations in 3 unknowns, that's what you need. But you have an additional unknown here, capital I naught. So I need to replace this one by an expression in terms of my mesh currents. What would that expression be? I naught is equal to small I1 minus small I2, exactly. Okay, so you're going to use that here and here. And you're going to have 3 equations in 3 unknowns, which are small I1, small I2, and small I3. Now, I want you to look at the rest of the solution in the book, okay, how they're solving the 3 equations simultaneously. And you get I1, I2, and I3. Okay. And then that's not the end, because what is it that we want from this example? Use mesh analysis to find the current capital I naught in the circuit. You still have to get me I naught, okay? And by this definition, we know that I naught is equal to small I1 minus small I2. So once you found these, then you can get that. In fact, while you're solving, you discover that you don't really need small I3. If you're able to solve and find small I1 and small I2,
That's all you need to get your I naught, which is what we're looking for in this circuit. Okay. So sometimes you have to be careful because you don't have to make the additional effort to find all the missing variables when in fact you don't really need that, because what we want is to find capital I naught. So we just need to find small I1 and small I2. You need the three equations though, okay? You cannot do it without the three equations. So you have to solve the three equations. But eventually, if you're able through those equations to find value for small I1 and small I2, then you use that for your capital I naught, and that's what you want. Any questions? Okay. Problem. Look at this one. I have a current source in the loop. You see that? You have a 5 amp current source here. If you want to write KVL, because that's the method, right? You have to go around the mesh, every mesh, and you have to write KVL. So if you're going around this mesh here, if you're going around this mesh like that, okay, and you're coming from here to here, you have a drop, and then from here to here, you have this this current source, right? And by definition, a current source tells you the current, but you don't know how much voltage is across it. So you cannot write KVL. Okay, so you're stuck now. We have to find a way to use the mesh analysis when we have current sources in the circuit. So we're going to contemplate two cases. Case one, when the current source exists in only one mesh. Look at that. This is the example that you have here, right? You have a current source in only one mesh, which is the second mesh. And when you have a situation like that, then the solution is already given, because look at this small current, the current small I2. If this is the current small I2, what relation can you draw between small I2 and the 5 amp current source? Exactly. I2 is equal to negative 5 amps, okay? So although you have a problem writing KVL, in fact, it's not really a problem, it's a solution, because the current source is already solving that equation for you. So you're going to write KVL for the first mesh in terms of I1 and I2. That's your first equation. The equation is going to be I2 equals minus 5. And there you go. Set the mesh current equals the source current. Obviously, you have to take the direction of flow of current into account, okay? So you may have a sign. Okay, so you write KVL around mesh 1, and then you let I2 equals negative 5 for mesh 2, and you're done. So this is how you cope with the presence of a current source. But that was the first case, when the current source was existing in only one mesh. It wasn't shared. If it's shared, it becomes a bit more difficult. Not more difficult, really, but it requires, like, you know, you have to know what to do, that's all. But it's not really more difficult. So, case 2, look at that. You have a current source which exists between two meshes. Do you see that? Okay. So, you can't write KVL around the first mesh because you have this current source. You wouldn't know how much voltage to put. And you cannot write KVL around the second mesh because, again, you have the current source. So now you're toast. You don't have any way to write your KVLs. So we're going to use a method that involves something called a super mesh. So what is a super mesh? This is the definition of a super mesh. A super mesh results when two meshes have a current source in common. Thank you very much. Okay, that's what the
Isn't I2 minus I1 is equal to
That's correct. But then how are we going to produce? That's just one equation. Still have to find a way to produce the other equation. Okay, so this is what we're going to do. Look at that. We're going to combine those two meshes which share a current source into a super mesh. So a super mesh is made by combining two or more meshes together if they have a current source shared between them. So this is your super mesh now. Okay, so I'm going to go around my super mesh and I'm going to write a KVL around that. So let's see. If I'm starting here and I'm going like that. My laser pointer is not functioning too good. If you're starting from here and you're going like that, what do you have? You have a voltage rise of 20 volts, right? Okay. And then I'm going to go from here to here. What do I have? I have a voltage drop of 6I1. Agreed? Now I'm not going to go down because now I'm going around my super mesh. So I'm going to go like that. And now here I have another drop of 10I2. Okay? Because the mesh current in this part is I2. And then I'm going to go down from here. And I'm going to have a drop of 4I2. Okay, so I'm able to go around my super mesh, and I'm going to apply my KVL with voltage rises and voltage drops, looking at the mesh currents wherever I am. So in here I have a rise of 20 volts. That's the first part. Here I have my voltage rise of 20 volts, right? And then the second part here, I have a drop of 6I1. So I have to be careful that in here you have this mesh current of I1 here. And then when you go there, you have the mesh current I2. So your current now is, so your drop now is going to be 10I2. Okay? And then you keep going. So wherever you are in the super mesh, you have to still write in terms of your mesh currents as you normally would. So that would be the equation. 20 equals 6I1 plus 10I2 plus 4I2. That's your super mesh equation. You still need another equation to be able to solve those two equations in two unknowns, right? So you're going to look at your shared current source. That's the one that caused you the problem in the first place. That's the one that's going to provide you with the solution. And that equation is going to be I2 minus I1 equals 6. Okay? Yes? Because look at the direction of your current source. Your current source is 6 amps flowing from the bottom to the top. Okay? So it's in the direction of flow of I2 and it's against I1. So it's I2 minus I1. That's equal to 6 amps. If you had a current source in the opposite direction, if your current source was flowing downwards, then it would be in the direction of I1 minus I2. Okay? So that's the equation that you have. I2 minus I1 equals 6. Now you have two equations and two unknowns. You can solve that. Okay. We have one example here. For the circuit shown, find I1 to I4 using mesh analysis. We're looking for the 4 mesh currents. Okay. You have two current sources, right? You have the 5 amp current source between meshes 1 and 2. And then you also have the 3I0 current source between meshes 2 and 3. So now I'm going to have a really big super mesh. Okay? Because I have to kind of have a big mesh where I'm not going through a current source. So this dotted red line shows you my big super mesh. And I'm going to have to write a big KVL there. So KVL around the big super mesh. If I start at the bottom left corner, and I'm going to, what do I have? I have a drop of 2. Okay. And then I keep going. Well, here, but I'm going to keep going. I have here a drop of 2I1. Okay, there's nothing going like that. And then I'm going to go like this. I'm going to go like this. Now here I have a drop in the direction of small I3, which is 4I3. And then I have to go from here to here. Now this thing, look at that. I have a drop here through my 8 ohm. And that drop is going to be equal to 8 times the current flowing downwards, which is 8 times I3 minus I4. Okay? Yes? Well, I have, okay. This is a current source. Okay, so I cannot go around the loop which has a current source. So at least I have to have these two together being a super mesh. But again, I have here another current source. You see this one? So again, I cannot write KVL and go through this branch. So I have to take an even bigger super mesh that kind of goes all the way around so that I wouldn't have to go through a current source. Okay, that's how you form your super mesh. And then as you're going around your super mesh, just writing KVL normal. Okay, does that answer your question? Yes, because you cannot write KVL by going across a current source or going through a current source. So you have to try to avoid your current source. This is how you make up your big super meshes. Okay, so I wrote my KVL by going around the big super mesh. So all of these is equal to 0. I didn't go through any rise. Now I need to write 3 more equations because I have 4 unknowns. So first I'm going to write an equation by going around the 4th mesh. Okay, so I'm going to go like that. I have a drop, which is 8 times I4 minus I3. And then in this direction, you have a drop of 2I4. And then finally, if you go like that, you have a drop of 10 volts. All of that is equal to 0. There. So this one is the super mesh. This one is KVL around loop 4. I still need two more equations. What am I going to do? Yes. I4, well, not yet. I'm going to get to that. But when you're writing KVLs, you need to have as many equations as the number of unknowns that you have. So here we have two equations. The missing two equations are going to come from those current sources that caused you a problem in the first place. Okay? Whenever you have a current source that forced you to go through a super mesh, that same current source is going to give you the answer. So here we have two current sources. The first one is your 5 amps. What can you write with this 5 amps? Let me just clean this up a little bit. Okay, look at your 5 amps. What equation can you write? What does 5 amps tell you? Yes? I2 minus I1 equals 5 amps. Excellent. Okay. From the 5 amps current source, I2 minus I1 equals 5 amps. So here this is equation 1, 2, equation 3, and then from the 3 I0 current source, what would the 3 I0 current source give you? I2 minus I3, exactly. I2 minus I3 equals 3 I0. Okay, so here are your 4 main equations. The problem here is with this, you know, because it's a dependent source, it introduced a new variable. I have to get rid of this one. And that's where your equation comes in. Okay, because now you have to write an equation where you can remove your I0. So I0, and that's given from this rightmost branch. I0 is this current flowing through your 10 volts. It's flowing in the opposite direction of your mesh current, but it's equal to the mesh current. So I0 is equal to negative I4. Okay, so you plug that in here, and you have in 4 unknowns. Okay, now this is the circuits part. After that, it becomes math, and you have to be able to know how you would solve those equations. You can go back to the textbook to see how the problem is solved after that. Okay, thank you very much. Yes.
Why do they